This is section 7.1, and we're talking about the area between two curves. Now, before I go through the formal definition of what it means to be between two curves, let's just talk about really quickly in Calc 1, we talked about the integral as the area under a curve. Now, we said under a curve, but we actually meant that it was between the curve and the x-axis. So, with that in mind, we're going to define the area between two curves in a similar fashion as the area between a curve and another one using integration. So, first, let's talk about what we mean when we talk about two curves, and we say that one of them is an upper curve and the other one's a lower curve. So what does it mean to be upper or lower? Well, if f and g are two continuous functions on a specific interval, and f of x is greater than or equal to g of x, that means the y values of this function are all bigger than or equal to the y values of this function everywhere in the interval. So for all x in that interval. That means that this function's y values are all above this function's y value. So this function's essentially above this one in that interval. It may not be everywhere across the entire, xy plane, but it is over that interval. Then the area of the region bounded by the graphs of f and g in that interval. So we say that in that interval we mean the graphs of f and g and the vertical lines x equal a and x equal b is going to be this integral from a to b of this upper function minus this lower function. Now in Calc 1, we did this. We did the area under a curve as just the integral. And technically we did this subtraction, we just didn't write it because it was the upper curve, f of x, minus the lower curve. My lower curve, g of x, just so happened to be this line y equals 0. So I just didn't write that f of x minus 0 business. So let's say that this is my upper curve, this is my lower curve, from A to B. This region right here, the area of that region, would be given by the integral from A to B of f of x minus g of x. We say that's my upper curve, g of x is my lower curve. Now really all we're doing, because we're using integration, we really are just doing these Riemann sums. We are just finding the these little rectangles, the area of these little rectangles of infinite width, because we're taking the limit as that width goes to 0 and just adding them up. So this is very similar to the technique that we used in Calc 1. All right, so let's see some examples. Let's find the area of the region bounded by y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So the most important thing about this is going to be getting the region correct. So I'm going to ask you to sketch the region and shade it so that I know that you're finding the area of the correct region. So you can use your calculator to help you with these, but you can also use some of your knowledge of previous algebra courses to know that that's a parabola moved up 2 units. That's just a straight line with a slope of -1 and a y-intercept at 0, 0. And those two are just two vertical lines. X equals 0 is better known to its friends as the y-axis. Then we have x equals 1 over here. So this red stuff right here is my region of interest. So the area of this region would be the integral from 0 to 1 of this upper curve minus this lower curve. Now with this, in this chapter, I'm not going to ask you to integrate these by hand. I do want you to use the calculator's integration capabilities for this. So let me show you how we're going to do this. what we're going to do is put this integrand in to my y equals screen. So I have x squared plus 2 minus negative x. And of course, you can go ahead and put plus x in there if you want to act like an algebra guru and say, you know what, I don't want to type minus and negative. I'm going to go ahead and put that a plus. You absolutely can. Then let's go to second and then trace. You'll see that option number 7 has the integral of f of x dx. This graph is not going to match this graph, okay? That is because this is the graph of this function, okay? The area between this function and the x-axis is the same as this area right here. This graph is not going to match this one, so do not be alarmed when those don't match up. They shouldn't. Now it says lower limit, okay, we know that that's 0. Upper limit, 1. It's going to shade a little region for you, and we get about 2.83. So just put a little bar over there to show you that it was repeating. So we are going to use the calculator a lot in this chapter, right, for all of these, because setting up the integral, especially when we get to the word problems in the work and fluid force, just setting up the word problem is going to be tough enough. All right, so let's do another one, and I'll show you some more, more capabilities of the calculator as we go along. All right, so let's find the area of the region bounded by y equals 2 minus x squared and y equals x. You'll notice that there's no x equals a, x equals b given. That's because those two intersect, and we're just talking about the area of the region bounded by these two. So these intersection points are going to define my upper and lower bounds. Now let's talk about how I got this graph. 2 minus x squared, you can put this in your calculator as well. It is just a parabola that's been shifted up 2 units and flipped down. So that's why this looks like this. Y equals x, of course, is just this diagonal line. Slope of 1, intercept at 0, 0. Where did these points, these intersection points, come from? Well, there's 2 different ways you can do this. You could set these two equal to each other and solve, which I do down here. So, if I set these two equal to each other and go to solve this, you can see I can solve this by factoring. I could have also used the quadratic formula, completing the square, but I get those x values. And so an x value of 1, I could plug in 1 to this function or to this function. Oops. I can plug in 1 to this function or this function to get that y value. It's probably easier to plug it in this one. So I get those points. I'll show you how to use the calculator as well for that. So there's our region. All right, so that means that the area between these two curves is going to go from -2 to 1. So there's my bounds. And then it's going to be my upper curve minus the lower curve. So I've got this upper curve, which is the 2 minus x squared, minus my lower curve, which is y equals x. We go to evaluate this integral. I need to put in 2 minus x squared minus x. Now for this x variable, I am using this variable key, the one that says xt theta n. If you're in function mode, that's going to be an x variable for you. All right, we're going to go to second trace, option 7. Remember, this is not going to be exactly this. There might be a little similarities, but it doesn't have to even be anywhere similar. All right, the lower limit is -2. I'm going to hit enter. The upper limit up here, on my integral is 1. So I'm going to hit 1 and enter. And I get that this integral is 4.5. So that area right here is 4.5 square units. Now, how can we find these intersection points if it's not, I don't want to say easy, but, this is not too terrible to have to solve to find those points of intersection? Well, let's go back into that y equals screen and put these functions in separately. So 2 minus x squared and y equals x. So we'll hit graph. Get a little bit of a glare from the light from this, so I'll turn that thing off. So that's what it looks like. Let me zoom in a little bit because that's a little zoomed out. So I'm going to get zoom number 4. Zoom decimal is about 5 in each direction. Alright, so that's a lot closer in. I don't want you to use the trace feature on this because it is not accurate. Alright, I want you to use the intersect feature. So same menu where the integral is, you'll see number 5 says intersect. So it's going to ask you for your first curve, and it's all blinky blinky on that top one. I've only got 2 curves in there, so I don't even have to worry about it. This is only a problem if you've got a whole bunch of different curves and you have to sort through which one's your first and which one's your second. So this one, I'm just going to hit enter. Yep, that's my first curve. It's all blinky blinky on this straight line, y equals x. Yep, that's my second curve, so I hit enter. Now, it asks me for a guess. So it's asking me, hey, get me somewhere in that vicinity. You'll recall from Calc 1 where we did that Euler approximation thing where we had a guess and then we used a tangent line to kind of refine our guess. That's what the calculator's doing. So it's like, hey, could you just point me in the right direction? Because there are 2 intersection points. So let's go back here and let's just say you look at this one and you're like, I don't know, maybe -1. So you just throw it in the right direction. And it says, okay, it's -2, -2. Boop. Let's go through that again for the other intersection point. So option 5, first curve, enter. Second curve, enter. Now the guess, let's go after this point over here. Let's say you look at that one and you're like, man, that looks like it's at 1. So you say x equals 1. You hit enter and it says, yes, it is x equals 1. And so you get the point 1, comma 1. So there's that point right there. So you can use the calculator to find the graphs to help you graph this thing. You can use the calculator to help you get these points of intersection. You can use the calculator to evaluate this integral. Now that might scare you a little bit. Maybe like, what on earth is coming in this chapter that she's letting me do all this stuff on the calculator? It can get kind of messy. Getting this set up and everything is sometimes the really messy part. Alright, let's look at another one. Speaking of getting messy. The area of the region bounded by x equals y minus 2 and x equals 4 minus y squared. Now with this one, because it gives these functions to me as x as a function of y instead of y as a function of x, I really have 2 approaches that I can do. Okay, and it's really going to be up to you. I'm going to do both approaches and kind of let you pick your favorite. All right. You could graph these by solving both of these for y. Just add 2 to both sides and get y equals x plus 2 for this one. Subtract 4, divide by -1, and take plus or minus the square root. Okay. You could do that. I'm going to do that technique in example 4. A different way of doing this, and this technique I'm going to do for this example, is going to be useful if it's not easier to solve this for y. Alright? Instead, here's what I'm going to do. I'm going to graph y equals x minus 2 and y equals 4 minus x squared, and then rename the axes. So what I'm going to do is graph these on my calculator, or how I know that they're going to look. That this is a slope of 1 and y-intercept, you know, down there at negative 2, at 0, negative 2. And this is a parabola flipped over and shifted up 4 units. And then rename the axes. Now I'm renaming the axes, I'm flipping the axes because I flipped the variables. So that's what's really, this technique is really weird. Not always my first choice for how to graph these, but I want to present it to you. All right. So here's what I did. So for here and here, so I interchanged the x and y from the original functions. Alright, so that this one, y equals x minus 2, looks like this. We know what this looks like. You know, y equals x minus 2, we know it's just a straight line, slope 1, y-intercept down here at 0, negative 2. This one, like I said, parabola flipped down, shifted up 4 units. So the region between those is the area that we're looking for. Because I changed the variables from the original functions to these to make them easier to graph, I changed my axes. This is my y-axis, this is my x-axis. So when we go to find the area, the integral is going to go from negative 3 to 2. Now, where did I get those intersection points? I'm glad you asked. I got it from the calculator. Let's go to the y equals screen. And our calculator is only going to graph functions. When we graph, this one especially is not a function. So that's why your calculator won't graph it. So that's why we had to flip that variable in here to get it into something that your calculator will graph. Although I say that, you can make your calculator graph it by doing it in 2 pieces. I'll show you that in example 4. I'll stop rambling. So y equals x minus 2 and 4 minus x squared. Let's see what that region looks like. That's not a really good zoom for this one, is it? Because we can't see that intersection point down here. We can see this one. This one really looks like it's happening right there on that axis. Let's zoom out. So I'm just going to go to zoom 6. That's zoom standard. That's 10 in each direction. Alright, so that way I get a full view of that area that I'm looking for. Let's use the intersect feature to find those points of intersection. So number 5, let's intersect. First curve, just going to hit enter. Second curve, enter. Guess. Let's see. This one, let's just say negative 2. Alright, so then it comes back and it says, nope, it's negative 3, comma, negative 5. Okay. Let's find the other point of intersection. That one looks like it's right there on 2, 0. So let's go number 5. First curve, second curve. I think I skipped that part. Let's hit 2. And yep, sure enough, 2, 0. Alright, so that's how I got those points of intersection. Now the question is, why did I put a little negative 2 right there when that is obviously a negative 3? And I did not even use an erasable pen on that. I'm glad I caught that. Okay, so that's a negative 3 right there. So, oh actually, you know what, that is a negative 2. Darn it, because that's the, I labeled that point right there, that x-intercept for that parabola. Negative 3 is back over here. This is just not drawn to scale. Alright, anyway, back at the home front here. The integral is going to be from this intersection point of the two curves, right? This kind of end point of this region. So from -3 to 2. Boop, boop. And then we have our upper curve minus our lower curve. So my upper curve is this 4 minus y squared. My lower curve is this y minus 2. Now you'll notice that I went back to the y form of these curves. Right? I only used this to get the graph. I'm not actually going to use this for my integration. So really what this is all a function of y over here. And look, this -3 and this 2 right here, those are technically y values because they're on this y-axis. So I just want to point all that stuff out to you there. Okay, so when we put this in the calculator, you may say, well, you don't have a y to put in the calculator. That's okay. You can just use x. If the variable of integration is different than x, you can just use an x in there. So let's do 4 minus y squared. I swear, I hit record and I swear, I closed my door and the dog always has to be on the other side of whatever door is closed. And so she's all scratchy, scratchy, scratchy. One would think that my children would be the problem with me hitting record, but oh no, it's the dogs. So back over here we got 4 minus x squared minus this entire quantity of y minus 2. Now again, we don't have a y variable, so we do have to use x. Also make sure that you put parentheses around here because you are subtracting this entire quantity. If you wanted to clean up this integrand before you put it in the calculator, that's okay too. You could distribute that minus, combining like terms. You can do anything, any of that simplifying beforehand, or just make sure you're careful when you put it in the calculator. So there we go. We got that 4 minus variable squared minus variable minus 2. We're going to go to second trace. Option 7 is my integration. Remember, this is not going to line up with this one. It's not going to be the same graph. And I'm going from -3 is my lower limit and 2 is my upper limit. And I get about 20.83 repeating. So this is one of the ways that you can handle it if you come across functions that are given to you as x as a function of y instead of y as a function of x. The other way, as promised, for example 4, is going to be to just solve those for y. So this one, I'm giving it to you as a function of y. So this would be the same thing as x equals y squared plus 1. X equals 0. Now, to graph these, I go ahead and solve them for y. Now really, the only one I have to solve for y is that top one. Everything else is not really a problem. X equals 0, I know how to graph that. That's just the y-axis. I know how to graph y equals -1 and y equals 2. They're just horizontal lines. So it's really only this thing right here. So taking this function, and you know how we have f of x and we change it to y? Well, f of y is going to change to x. So taking this and solving it for y, I'm going to subtract 1 over, and then I'm going to have to take the plus or minus square root of both sides. So what this is going to be a sideways parabola, which is not a function. So your calculator will not graph it as a function, but it will graph these two pieces individually for you. So let's see what that's going to look like. So if we graph the square root of x minus 1 and the negative square root of x minus 1, you can see there's the top half of the parabola and there's the bottom half of the parabola. Let's zoom in a little bit. It's kind of far out. So graphing this entire region, that first that f of y equals y squared plus 1 graph is this parabola opening to the right. X equals 0 here is the y-axis. Y equals 2 and y equals negative 1. That gives me the region bounded being this area right here. It's really important to me on these throughout this chapter that when we have a specific region of interest that you guys sketch that region for me and you shade it. That way I know that you're looking at the right region, because if you're looking at a wrong region but you set up the integral correctly, you integrate it correctly, you do everything correctly, I'm going to give you a lot more partial credit, right? And it's going to help me know where you went wrong. Whereas if you just set up a bad integral and I'm like, I don't know what went wrong here, so I just need to see this as part of your work. Now, when we go to do this, normally we would go upper minus lower. And then we would have these bounds from, left to right. But those left to right bounds there, that's not a straight line. And my bounds, you'll notice, are always those straight lines. That's because for this region, I'm going to have to add up my rectangles sideways. Because this was given as a function of y, right? It was given, the original problem was given to me as x equals a function of y. All this stuff is going to have to happen as a function of y. Because I relabeled my axes last time, I was still able to do upper minus lower because my axes were flipped. This time I'm leaving my axes as, normal x, y. So here I have to go right curve minus left curve. So I've got this y squared plus 1 minus 0, and that's going to be integrated from negative 1 to 2. I did not have to worry about right and left with my last example because I interchanged those axes. So my upper minus lower was still all about the y's. It was all about those y variables. Even my bounds, remember how I said that those bounds were still y points? That went from negative 3 to 2. That was still a y point. So for this one, my upper and my lower technique still worked because I flipped those axes. If I had changed this, like I did for example 4, where I solved them for y and graphed them, then I would have to do the right minus left business. So there's a small perk to doing it this way, in that you get that upper minus lower thing kind of, stay put. That technique kind of remains. But really, if you look at your upper minus your lower here, you'll see that we've got these straight lines. That's usually an indicator that, something's a little off, right? You always kind of want to go from, one curve to the other within those bounds. So we take right minus left. That's because right is bigger. We know that on the x-axis, farther to the right is bigger than an x value that's farther to the left. So my right curve is this x equals y squared plus 1. This curve right here is 0. That was my f of y minus g of y. And that's going to be from negative 1 to 2. Those are y bounds. And just like before, when we put this in the calculator, we are going to have to use the x variable. If your calculator has a y variable, awesome, use it. I'm not going to put minus 0 in there. You guys know that we don't need that. So let's go to option 7 here. And we're going to integrate this from negative 1 to 2. And so we get the value of 6. square units for the area of that region. All right, one more example, and this one's going to have some Calc 1 stuff built into it. Set up and evaluate the definite integral that gives the area of the region bounded by the graph of x cubed minus 2x and the tangent line to this graph at negative 1, 1. All right, so we got to dig deep into our Calc 1 knowledge here, all right? First, we need the equation of the line that's tangent to x cubed minus 2x at negative 1, 1. So if we need a tangent line, we need a derivative. Why? Because the derivative at a particular point is the slope of a tangent line. So I took this derivative, so 3x squared minus 2, the slope of the tangent line. That's how I write this. So m meaning slope. This little tan is just an abbreviation down here to say it's not just the slope of any line, it's the slope of that tangent line. So all I did was take this slope and I plugged in that x value right there. And I got 1. Now you'll notice it's in a different color. You'll see why in a second. To find the equation of a line, we have the point slope form of a line. So that's just standard equation of a line. You could also use mx plus b if you wanted to. So in point slope form, I just have to plug in a point and the slope. Well, I've got the slope right here. That's my slope of my tangent line. This is the point at which, things are happening. So you can see how I color-coded this. So just plugging that in and doing some simplifying. Of course, that's going to be a plus. I don't have to write that 1. I can add that 1 over. So here, now we got this into a problem that we can handle. Because now that all this Calc 1 stuff's out the way, we want to find the area of the region bounded by this polynomial curve and this line. I just had to find this line to begin with instead of being given it. So all this stuff right here was just to get that line. Now we're just like we were with the others. Let's graph these two and see what it looks like when they intersect. So the x cubed minus 2x graph, that is a polynomial. So we got a little swoopy thing going on here. And then the other one's just x plus 2. That's just a straight line. So it looks like that. My zoom is not really good on this one. You can see that it kind of grazes right here. Now, is anybody shocked that this x plus 2 line just kind of smushes up against that, just kind of, kisses it on its way by, kind of smells its hair and is a little weird on its way by? No, we know that's going to happen because we just spent an entire page finding the equation of that line that's tangent to this swoopy curve at that point. So of course that's going to be tangent right there. Of course it's going to just touch it right there at that single point. Duh, of course, right? All right, let's zoom out so we can get a little bit better idea of where that other point is. All right, so we've got this tangent point right here, and then we've got this other intersection point, so we want the region bounded by that. So we want that red region right there. Let's find those points of intersection. I already have them labeled, but you guys know how to do this by now. We're going to use option 5. The first curve, enter. Second curve, enter. Guess. Let's say that back here you put negative 2. Ooh, that's interesting. I did not see that coming. I put negative 2 as my guess, and it took me all the way over here to this point of intersection from 2, 4. Ooh, that's cool. You know why it did that? It did that because of that Euler approximation technique in Calc 1, because this so happened to have this intercept back here at negative 2, so it hit that line, followed that tangent line over to here. Oh, that was kind of cool. Very unexpected. So we get that intersection point. So let's do this again and get the other intersection point here. First curve, second curve, and let's say -1 this time. And sure enough, we get -1, comma 1. Sorry, I'm just nerding out over here on you guys. All right, so my integral is going to be from -1 to 2. And it's going to be my upper curve minus my lower curve. You can see this upper curve is this straight line, this x plus 2. The lower curve is my little swoopy guy here of x cubed minus 2x. And then we're going to go back here. I'm going to clear those out. I'm going to put in this integrand. So that's the x plus 2 minus that quantity x cubed minus 2x. Let me check it real quick, make sure I typed it in right. You don't have to put parentheses around this in your calculator. The parentheses really only make a difference after this minus right here. So that, and the lower limit is -1 right here, and the upper limit is 2. And so I get 6.75. Right there, 6.75. Now, with this one, if you did not, prior to this one, if you did not want to use the intersect feature, if you were like, you know what, I'll just set the two functions equal to each other and just solve it to find those points of intersection. This one, you almost have to use the intersect function, because setting these two equal to each other and solving this, oof, it is not pretty, all right? Why? Because to solve this, it doesn't factor nicely. You move all this stuff over, and basically you get a polynomial equals 0. You got to find the zeros of a polynomial. And you may recall from such hits as college algebra that is not pretty. There was like synthetic division involved and stuff like that. So it was ugly. Or you end up just using your calculator to find the zeros of this when you could just use the calculator to find the points of intersection of this. So. Okay, at long last, that finishes up section 7.1.